In my last video, we talked about how a spacecraft lands on the moon, but I kept things pretty simple. But this time, we're diving deep into the details. Everything from the critical phases of the descent to the complex calculations behind a successful landing. Step 1. Before the launch, several crucial preparations need to be completed, including fueling and system checks. The rocket is fueled with a combination of liquid oxygen, or LOX, and either kerosene, or RP1, or liquid hydrogen, or LH2, depending on the stage of the rocket. Once fueling is complete, all systems undergo through checks to ensure everything is ready for launch. All rockets rely on Newton's third law of motion, which states, for every action, there's an equal and opposite reaction. In a rocket engine, fuel is combusted, and the gases produced are expelled at high speeds from the engine's nozzle. This exhaust creates an upward force, or thrust, that pushes the rocket off the ground. The thrust generated by a rocket engine is given by this equation. F equals mv plus A times P1 minus P2, where m is the mass of the gas ejected per unit time. V is velocity of the gas. A is area of cross-section of the nozzle. P1 and P2 are the pressures of the exhaust gas and surrounding atmosphere. Step 2. To leave Earth, the rocket must reach a high enough velocity to overcome Earth's gravitational pull. This minimum velocity is called escape velocity, which for Earth is about 11.2 kilometers per second. The formula for escape velocity is VSC equals the square root of 2gmr, where g is the gravitational constant, m is the mass of the Earth, and r is the radius of the Earth. Once the rocket leaves the atmosphere, it doesn't head directly to the moon. It first reaches Earth's orbit. Most rockets enter a low Earth orbit, or LEO, which is at an altitude of about 200 to 400 kilometers above Earth's surface. The rocket needs to reach a high horizontal velocity to enter orbit, not just go straight up. For Earth, this is about 28,000 kilometers per hour, 17,500 miles per hour. This speed ensures that as the rocket falls due to gravity, the curvature of Earth causes it to continuously fall around the planet rather than back to the surface. In orbit, the rocket follows Kepler's laws of planetary motion. The trajectory of the rocket becomes an ellipse, with the Earth at one of the focal points of the ellipse. Most rockets use multiple stages to shed weight as they ascend. Once the fuel of the lower stage is used up, it detaches, and the upper stage continues the journey. This makes the rocket lighter and more efficient. When the rocket reaches the right altitude and speed, it shuts off its engines. The spacecraft is now in freefall around Earth, continuously moving forward fast enough to stay in orbit without falling back. Step 3. After entering orbit, the next step is to propel the spacecraft from Earth's orbit toward the moon. This maneuver is called the Translunar Injection TLI. During TLI, the spacecraft fires its engines to increase its speed and follow a trajectory that will take it to the moon. The spacecraft's trajectory and timing must be precisely calculated to ensure that it enters the correct path toward the moon. This burn point is called the perigee, which is the point in the spacecraft's orbit closest to Earth. The speed required for TLI depends on the position of the moon, but is generally around 10.9 kilometers per second. Most TLI burns are initiated from a circular low Earth orbit, around 200 to 300 kilometers altitude. The altitude of the starting orbit influences the delta V, as a lower orbit requires a slightly higher delta V, due to the stronger gravitational pull at lower altitudes. The path from Earth to the moon is often described as a Hohmann transfer orbit, an efficient way to transfer between two orbits using two engine burns. The first burn, TLI, moves the spacecraft from Earth's orbit to an elliptical orbit that reaches the moon. The second burn happens upon reaching the moon, adjusting the speed to enter lunar orbit. Step 4. After TLI, the spacecraft coasts through space toward the moon. This part of the journey takes about 3 days. During this time, gravity from both Earth and the moon act on the spacecraft, but the spacecraft follows a curved path, trajectory, towards the moon due to its initial velocity. This part also known as free return. This type of trajectory is important for safety, especially in case of system failures. For example, the Apollo missions used a free return trajectory during the initial phase, so that if there was an emergency and they couldn't complete the mission, the spacecraft would still automatically return to Earth. In a free return, gravity does most of the work after the spacecraft's initial injection burn, which minimizes fuel consumption and ensures a safe return in case of malfunctions. As the spacecraft nears the Moon, it performs a maneuver to enter lunar orbit. Here, the spacecraft's velocity must be adjusted, usually by slowing down, so that the Moon's gravity captures it into a stable orbit around the Moon. The spacecraft's main engine is fired in the direction opposite to its motion. This is called a retrograde burn, or retro burn. The purpose of this burn is to reduce the spacecraft's speed so that the Moon's gravity pulls it into orbit, rather than letting it escape or crash. After the retro burn, the spacecraft's velocity decreases, and it is captured into an elliptical or circular orbit around the Moon. The exact parameters of the orbit depend on the mission goals. For landers, orbiters, or crewed missions. Step 5. When the spacecraft is in orbit around the Moon, it is typically in a circular or elliptical lunar orbit, altitude of approximately 100 kilometers. The spacecraft needs to slow down to begin its descent. At a specific point in the orbit, typically at the periapsis, or the closest point in the elliptical orbit to the surface, the spacecraft begins its powered descent by firing its descent engine to slow down further. This is done to cancel the forward orbital velocity and allow a controlled vertical descent. In this phase, the spacecraft further reduces its velocity to near zero. The engine continues to fire, and the velocity change required here is significant since the spacecraft is close to the surface, requiring precise control. The Moon's gravity is about 1/6 that of Earth's, so the spacecraft doesn't need as much thrust to slow down and land. For the descent, the rocket must balance the thrust and lunar gravity. F equals mg, where F is the force or thrust. M is the mass of the spacecraft, and the g is the gravitational acceleration on the Moon, about 1.62 meters per second squared. To control the descent rate, the thrust must be adjusted to be slightly less than the weight on the Moon, allowing for a gradual reduction in velocity. Finally, as the spacecraft nears the surface, it uses small thrusters to reduce its speed to almost zero for a soft landing. Astronauts, such as those on the Apollo missions, have made these final adjustments manually in the past, fine-tuning the spacecraft's descent. A controlled burn using descent engines slows the spacecraft to achieve a soft landing on the Moon. The required delta V is about 1.6 to 2 kilometers per second. The descent trajectory is carefully planned to ensure that the lander doesn't approach too steeply or shallowly, both of which could result in a crash.